you may think if you're joining us on Twitch land that we're starting late. You would be incorrect. We started as soon as we could, and I got to show a nice demo of my computer hard locking when trying to use dtrace on it. The folks in the room got to see that nice demo where I proved that it definitely did not work and is incredibly annoying. So this is why we're not doing dtrace today, like I said we would start out with doing. But I guess first order of business, did I disable alerts? I did not. There will be a new module launching that is very fun, I think. I think you'll agree. So there is, yeah. So we have the mock IPC. When you've been doing IPC, thank you all for your help with helping me debug these things that do and don't work. Now you can see everything works. So you can pop things, figure out how to send messages. This can get very in-depth. The next thing we're going to do is use the mock ports that we talked about last week. So specifically, like when you get access to the task ports, what are the different things you can do? Getting access to the host port, and then getting access to the exception port. So all of these should work. I've tested them as well as I could. The exception port was a massive pain in the butt. Sending a port right across was like a classic thing, technically easy, but then as you do it, you make one stupid mistake and then it takes you a day and a half to figure out what that mistake was. It was very embarrassing, but I did fix it. It does work and you can pass. And it was also very difficult to debug. Like I mentioned, the exception port is what the debugger uses. So when this challenge creates a new port, sets it as the exception port, and then moves the receive right to you. But as soon as you do that, then you can't debug anything anymore. And so why it wasn't working was very confusing and took a long time to debug. So that should be fun. Questions on this? Still not able to get, I think the other cool level to have here would be the kernel, getting the kernel task port. The problem is that would require writing a kernel module, and I'm still not 1000% certain how kernel modules are going to work in this system because kernel modules need to be linked into the kernel, and so I don't know if I can easily do this of basically having the kernel module, when your VM starts up, it checks if there's a kernel module, it installs it, and then tells it to reboot, so it actually reboots with the kernel module. I hope that will work, because then otherwise I have to bake in the kernel module for each of the different versions, and then I've basically got all of these different 50 gigabyte base image versions, depending on which ones have which kernel modules in. And then when one of you finds a stupid workaround for the crappy startup script I have that lets you get the flag, then I have to update every single one of those, and that sounds horrible. So I really don't want to go down that route. So I hope there's an easier way. And I'm still not sure how you're going to get debugging working yet. So in the kernel, so I don't know. Maybe that'll be through because there is, which one of them did it? It was iOS. GitHub. What? A normal what? No, you can't run this in QEMU. You can kind of run it. This was my very first thing I tried over the summer. You can get, if you look it up, if you're interested, QEMU, Mac OS. Of course, I messed that up. Yeah, there's this one, OS X KVM. This runs, I believe, in x86, so you don't have ARM, which is kind of one of the whole points of doing all of this. There is, which would surprise you. Wait, is it BlackBerry, or what's the name of the BlackBerry? Yeah, BlackBerry's blog. So this is, as you can see, all of these links have already been visited because I've seen these many times. So this is a really cool thing where they can get XNU booting up to Bash. So you can use Bash in here, and you can do this. It does work, but it is hard-coded for a specific kernel version, and they have to do in-memory patching of instructions of the kernel to even get it to this point. And I played with it, and getting it even farther is you just hit some weird kernel infinite loop, and then like I have no. Yes, it was far too crazy to get it anywhere further. I think we can do this. Okay, so the thing I was trying to find here, and I think we'll find this. No, where was? Yeah, there we go. KTRW. This was the thing. So this is actually an iOS kernel debugger that, yeah, Brandon Azad wrote when he was at Project Zero. That basically was a. So this was, oh yeah, they used debug registers that were on devices to like, yeah, so they use this bypass to load a kernel extension that implements a GDB stub, which then gives you full-featured kernel debugging. So maybe we can load this as a kernel module in our thing to give us debugging into our own kernel. I have no idea, but this could be a fun, maybe this will be the route we take, but yeah, it's gonna be a journey is the goal. Okay, any other questions? I don't know what I was talking about. All right. What are we learning about today, chat? We are not learning about dtrace. We are learning about the allocator. So we're diving right into the heart. We are going to look at, I will spoil it, but much of this is based on a great blog post that I think I mentioned already. That's on the Apple Security blog. This is from October 27th, 2022. It talks about what they've done in the kernel and things that they've done to improve the safety of the kernel. So today we're going to be doing like a deep dive. We're going to be talking about how it works at a high level. We're going to be looking at code as much as we can. There are still parts of the code that I cannot find that should be doing some stuff that I don't really understand where it's being done. But, you know, mysteries are always fun. And as you can imagine, there are several different types of memory allocation in a kernel, right? You have the virtual memory management system that has to allocate physical pages, right, that are actually resident like on the machine and give them to different people or tasks like kernel things that ask for them. From there, there's also, you may need something just like malloc, where you say, hey, I need 16 bytes. I don't need a whole page of memory. I just need like 16 bytes. Just give me like a malloc call. So there's different styles of things. We're going to go into like the malloc style kernel allocator, which we'll see has different things. So this uses a slab-based allocator, but before we get into that, somebody describe how does like libc's, like glibc's allocator work? Was it? Yeah, but that's what. How does it like? If I don't know what that is, how would I know what that is? Yeah, so it divides. So it takes the heap, and every time there's an allocation, it tries to say, okay, let me carve out some space on this heap. Let me give it to you, and I'll put some metadata there so I can know the size, everything like this. And then it has to deal with freeing things, and so it has to handle different size allocations. It has to handle, you've talked about coalescing, when like if you have multiple freed blocks that get together in one chunk, you want to free all of that. It has to deal with, but of course that has performance problems. So then you have things like the T-cache to like cache recently freed memory so that you can just reuse it quickly. Operating systems also have the same problem. Right? You have data structures as a user space program talks to the kernel, right? The kernel usually has to allocate memory for that request. Any networking that happens on your computer, right? Like networks requests are happening all the time. The kernel must maintain at least the 4 tuple of like IP port and source and destination of both. And so it has to maintain all these things. There's a lot of things that continually happen. And if your allocator is very slow in the core of your kernel, you will have problems. So one of the big, I believe, yeah, the Linux allocator, which I'm not as familiar with, is based off of this like same slab style of allocation. So this was an idea that was proposed in like early Solaris in 1994. What I think is super cool is if you're like interested in these concepts, there's like reading the code, which is nice, but then you can also go read this paper, which talks about their approach, why they decided to design these things in these ways. So that's why I think it's interesting and nice for you all to look at these kind of things. So, but the core idea is basically like, how can we increase the speed of allocating and freeing memory? And I like to think of it by like simplifying structure. So basically, rather than saying that you can do arbitrary size allocations and then we'll cut it up very specifically and give you exactly what you asked for, what if we only provide fixed size allocations? Like, you can't necessarily ask us for any size, or if you do, we'll just round you up. So if you ask for 12 bytes, sorry, the smallest we give out is 16 bytes. So you'll just get 16 bytes of memory. Your program should, or if it's a kernel process or whatever, it shouldn't care because it only accesses those 12 bytes because that's what it asked for. So rather than supporting arbitrary size memory allocations, you can do fixed size. The other thing is you can think of, or I think of it as like pre-allocating the memory for these different sizes, so they're kind of ready to go as they're being asked for. And so each slab we're going to transition kind of terminology here as we get closer to what like XNU calls things, and even then it's like slightly different between like the conceptual, like what is a slab allocator and what does these specific things do. But these are basically the specific sizes. I guess I should have done this in hex. This would have been probably nicer to look at, but I'm sure some of these numbers pop out to you as very nice round powers of 2, right? So essentially you can think of it like there's some kind of slab or some kind of allocator that's dedicated towards each of these sizes. And let's see, we'll see, but the compiler knows the way they've done allocation is when you ask for something, you also ask for the specific size. So it knows, it either looks up the zone, or oftentimes it's actually pre-computed of which zone these things come into. So you can know, okay, I have this size object, this is what allocator I'm going to talk to. So this is where we're going to transition. So XNU calls these zones, and their zone is more generic than size. The zone has to have a size, but it's not like there's one size for one zone for exactly one size. You can have you can have different names for zones. So you can have 100 different size 16 zones. I was going to get to it. Well, we'll get to it later. So, and we can even look at this without anything. So actually do I want to do this on the actual thing? Sure. All right. And say it again? It's more than 100 bits, I guess. Yes, kind of like bins, exactly. But there is no fallback. Well, the fallback is if you need more memory than that, which is a natural question, you get like a virtual memory address basically, and it happens at a different level. But that's kind of outside what we're going to be looking at. Okay, let's SSH hacker app. Oh, I didn't tell you the story of why SCP and rsync and all that stuff wasn't working. It was like a nightmare to track down. But anyways, so there's a handy dandy zprint. So there is a nice handy dandy used by root, so normal users can't access this information, but there's a nice zprint. I guess you can think of this as zone print, not whatever I typed in that was incorrect. So this shows you information about the zones that are already so he calls it like allocation buckets. So we can do something like, and that looks ugly, so you're gonna have to deal a little bit. Come on, so close. Okay. So you can see there's names like vm.permanent, vm.per.cpu, the element size 1, that's weird. These are like most things. I have no idea what a lot of these things are. Let's see. Oh, I mean, I think, yeah, even when we looked at this, we saw that like the allocations for tasks were happening in a special like task. You can see like ipc.ports. Ports are happening in their own zone. So ports are 144. And you can even do like you could check that this is working by like allocating a ton of ports in a user space process and then running this and seeing that like, yep, there are stuff that's happening in the kernel. Let's see. Yeah, you can see there's 8,763 current elements. Oh, we're already at max. Oh, wait, I see. We have current in use. So you can see which ones are free. Wait, what? Alloc count. This is. Anyways, well, you have to dig in and figure out exactly what all of these are. I don't remember exactly what these flags are, but there's a ton of these. So you can see like default.kalloc.whatever. This is the different size. This is 16, 16, 32, 32. And we'll get into what all these differences are, but you can see like so like size 16, there's this default kalloc 16. Here is data kalloc 16. Here is kalloc type 0.16. And so on. We're actually going to dig into these. This is the thing we're looking at today. And then a bunch of other stuff. I think some of these are kernel modules. You can get your own, as a kernel module, you can ask for your own zone of memory to use if that's something you want. Let's see. There is, I can't remember what all these are. So anyways, so you're going to introspect that from user space. And so the ideas and things to talk about, we have the zone. This is the zone T data structure. It's, again, dedicated to objects of a specific size. Let's actually go look at that. And I'm going to show you another cool thing. So I haven't installed it yet on these systems, but there is at a certain point when you have to use these, there will be a kernel developer kit installed on these things. So this is a KDK, which has, I think I showed this before. We're using 12.5. System library kernels. Yeah. So this is the thing that has different development kernels, KSAN kernels, release kernels. And the other nice thing in this .dsym, we're not going to go into it, but this is, you can think of the .dsym directory as like the dwarf header information. So this is like symbol information and other type of information that is super helpful. The other thing that it has in there, like kernel.release the dot after the release is different specific devices and device configurations. I don't remember what they all are. You can look at them online and they'll tell you, but one of them's like the laptop and there's I think it's like hardware specific things. I mean, since we're talking about it, let's look this up. T600. But tell me what these are and what they. There we go. Somebody's got it. Yeah, okay. So the T6000, M1, Apple M1 Pro. Let's see. Is there what was the other one we saw? T8020. T8020 is the A12, so the iOS kernel, iOS SOC. Anyway, so these are just specific to the different CPUs. It doesn't matter. I can't remember. Let me look at which one I was using before. Yeah. Oh, this was the one I was actually using. Let's do T6000. And then, we can look in dsym, in contents, resources. There's, I guess it maybe just is dwarf information. I haven't dug into these to figure out exactly what the format is. There is a nice, a bunch of Python code in here that is plugins and macros for LLDB. So we can boot up, and this is the reason why I'm showing all this, even though I started this off by saying I have absolutely no idea how we're going to get kernel debugging working, because you can boot up, let's see. Oh, thanks, Rob. So what, yeah, there we go. Yeah, so we can set this setting, run this, it loads all of the code and everything that we just put in there, all the Python code, and there's actually even super useful things that you can do that you can use without even running anything. One thing that I very much like is show struct packing. Especially, let me show, yeah, so we wanted a zone T. So it's just got, it's very similar to the GDB has what, the p-type/o. This is kind of nice. The -x actually controls hex alignments here, which is incredibly useful when you're doing things when not having to worry about decimal. But it's also a really cool way to like verify the thing you're looking at in source, how it actually compiled to the real system. So we can see the zone struct. So is a zone T is a type dep for a zone struct, which we'll see in a second. But it has a ton of information. It's what, A4. This is the other problem, of course, with hex is I can't intuitively tell you exactly how big that is. And another cool thing, it does the coloring, so you can see like padding. It like calls out to you where different padding is. It also unpacks things a bit, so we can see like here is the Z page EQ empty. Oh, this will come up later. And we can see that's at 74, and that's its own struct, which has some kind of packed address in here, which is only 4 bytes. That's interesting. Yeah, so it's kind of cool because it deconstructs all the structs, so you can actually see like everything in this type, what it all is. Let's see, yeah. So let's look at it in the code. And I was looking at this earlier. It's in zalloc.h. Okay, we are in 12.5 OSFMK kern, and zalloc.h should have everything that we want with kernel allocation. Is that good enough in the back? Big size? Good size? Bigger? You can say bigger. Okay, it's visible. Cool. All right, so we're gonna look at the zone T. Oh, I'm gonna have to change the color. Oh no, I don't have my history. Was it Calm Forest? Yeah. Oh, okay, back to here. At some point I will remember how to do this, but today is not that day. Wait, where's my struct? Internal. Okay, I swear that's why I put that in that slide, because I found it and was looking at it. Okay, this is extern zone T. These are just defining functions. Oh, there we go, okay. Okay, in kern types.h, there's a type def of struct zone to zone t. Okay, so what we really want is this, which I guess we knew from looking at the Nope, that's just a forward reference to zone. And give me a header. I feel like I'm going crazy. Okay. There we go. Wow. Stupid thing. Okay. Cool. So, one interesting thing from here you can read from these comments. The first 4 fields match a zone view. So let's look up a zone view, and actually let's just use our handy dandy. So a zone view is a pointer, or is a pointer to a zone T. It is stats about the zone, a name, and then a pointer to the next one. And we can see that the first 4 fields match that. So I guess for some reason you can use a view into a zone of a zone, like a zone itself can be its own view into it. I can't remember why, I don't want to, we could spend a lot of time trying to reverse engineer and figure out exactly why everything is the way it is, but we will definitely get stuck at some point. But I do want to just see the zone view T. So a view of a zone for accounting purposes. A zone view uses the zone it references for the allocations backing store, but does the allocation accounting at the view level. These accounting are surfaced by zprint and similar tools. That's interesting. So we at least can see where that information comes from. It must be those stats, these zone view stats. Cool. Okay. So that's just kind of interesting. Then there is, this is what's, so I was trying to look through some of this code this morning. It gets pretty crazy. You can do asynchronous expansion of the, by spawning a different kernel thread that runs, that does your allocations, like expansions for you. And that's what this expander is. You can have per CPU caches, which we'll talk about in a second, not like the details because I don't know them all, but there's just like on Tcache, right, is a thread local cache, which what's the point of Tcache? Why is it fast? Reduces contention if you have a super multi-threaded process. If you have one kernel allocation, sorry, not kernel in that case, but one heap allocation lock that every thread is trying to malloc and free things all the time, they'll be waiting on access. So by splitting it up into Tcache, where each thread gets its own little cache, they can each use from there. Similar thing here with the CPU. So you can have a CPU local cache that only each CPU uses that can speed things up. Let's see. Other thing, number of allocations per chunk, size of an element. So this is the thing that we saw, the element size. Bits. So if I can't remember, did we talk about this? Of this syntax? I don't think we've seen it yet. But this basically says I want a 64-bit unsigned integer here. But then, this is valid C. This is why, you think you know C until you start reading code from people who write operating systems and actually use C. This says I want a field called z_destroyed that is 1 bit. So the :1 means of the 64 bits, I want 1 bit that is this thing. And to call it this. So it's cool because on the field, you can just use that and the compiler will do all the masking and getting the bits for you and everything, and you don't ever have to worry about it. It's also, if you ever want to make a really annoying CTF challenge, this is a way to do that, of really messing with them about what the bits are and make it really easy for yourself. So you can see asynchronous allocation pending is thread waiting for expansion. Behavior, there's all kinds of stuff that you can, configure this zone with. We're definitely not going to get into all of these, I guess, permanent allocations. I'm not exactly sure when you'd want to do that. If you have the per CPU cache or not, this is like a bit that gets set. And if we look, we should see, yeah. So we can see this here. Wait, is that right? Yeah. So destroyed, async refilling, expanded weight, expander per CPU. Very confusing that it doesn't, this is not updated, and this size thing is definitely not right. So I don't know if this is like a, huh? The 64-bit type is, it just would be nicer if it like indicated that this was part of that, right? Kind of like here, right? Like it breaks down. It's, well, I guess this is a union, so that doesn't make sense. But yeah, here, this is a 16-byte struct, right? And the first 8 bytes are this, and the second 8 bytes are this. It would be nice if like it said, okay, there's a 8-byte uint64t, and then the first bit is this, and then this is 1 bit and 1 bit. Like these are all the named things. Maybe one of you can fix it and submit it. So the thing on the left is not changing though, because these are all the same: 3E, 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 3E. But it's not the exact bit offset, right? That'd be another way to fix it. Would be to say this is at 3A, this is at 3B. Wait, why does this say 3B? Oh, they're at this bytes. Yeah, yeah. Maybe you need like a colon there of like which bit of that byte or something. That's true. Yeah.
That doesn't make sense. If you scroll down further into the thing, I don't think it makes sense for the left-hand side change. When you start getting into those braces stuff, left-hand side is the byte offset
of the struct. So it makes sense of like, okay, all these, what is this? This should be 1, 2, 3, 4, 5, 6, 7, 8. Yeah, these are all 1 bit. There are 8 fields here, all there. Yeah, they're on the same byte, but they are then different bits of that byte, which, yeah, it's just a little bit hard to realize this is what's actually going on here for this byte. But so anyways, I don't know a better way. This is just my thoughts as I'm looking at these things. It's a weird thing, but it's, you can see it's very useful. And you can see like the reserved. So there's extra bits here that aren't being used that are reserved for later, that if they need to add more bits, they have 19 bits here that they can add here. Don't have to deal with the size of the struct changing. That's very nice. Okay, cool. So anyways, lots of stuff here. Locks always important. Yeah, other type of stuff, keeping metadata. We'll look at, I think, this one specifically. So anyways, we can see it's a big struct. There's a lot of stuff in it. And cool. Okay. And so there's a little bit of there's like a interesting different kind of nomenclature that gets used here. So it's called the slab allocator. So you think like, okay, like slabs must be involved, but a lot of the code and other types of things talks about magazines and caches and other types of stuff. Basically, the way I think of it, and the way kind of we really need to think about it at a high level right now is, so a zone can have like any number of pages, or you can think of them as slabs. So a slab could be a page, or it could be contiguous blocks of memory within a zone. It doesn't really matter, but that's like each slab is carved up into chunks based on the size. All right, so this is like where memory is allocated from, and because you're doing fixed size allocations, this means that you don't have to do any extra accounting, right? The only accounting you really need to do is which of this slab, which parts are in use and which ones are free. And so you can just give free ones away and then just use used ones. And then you need to keep track of a free list of some available chunks. So, okay, in this thing, what's available? So this did not work very well last time. I upgraded the operating system, so I'm sure it's going to get better. Let's gamble on having freeform working. course, as I say that, this doesn't even appear. I just keep like clicking on this. Why do they do this? Why is it so bad? Cool. Thank you. Okay. Hello. Are you going to sing Adele for us? Okay. So we can think of it as a very high level. We have a zone, and I know you can't. Oh, you can see it. Oh, that's quick. Can you see that? That's like instant real time. This is exactly what I wanted. You guys all saw that this did not work until I upgraded. Resist throwing my phone. Okay. So we have our zone. And so you can think of that the metadata now, rather than being stored in line with the objects like you have to do in the glibc allocator, can now be kind of stored all in one place. So you functionally, for the zone, you just need like, depending on how you want to do it, you can just say like some free chunk list, like a pointer of like some list of everything that points to the free chunks and other stuff. But essentially, you can even get away with a super stupid simple. So basically, you just get a page of memory, right? So you ask the other system for a free page of memory, and you just say, okay, I'm servicing, allocations of a certain size. I'm just going to split this memory up into this size, and I will create my free chunk list. Let's say each one of these will point to there, and then point to the next one, and then this points to here, points to the next one, points to here, points to the next one. Everyone see a classic singly linked list style thing? Good. Yep. So that's all in here. And then when I get an allocation, what do? Yeah, just boom. This goes right here, back where we want to go. Now this is no longer free. It's actually in use, so it's here. And then it's great. And then what happens when somebody frees something? Boom, just add it at the end. You can think of now we need a doubly linked list, but when this gets freed, we just have a link here, or we can even just push it on the front of our list too, so that way we can, that could be very fast as well. Basically like Tcache, right, in some sense. What happens if if our free list is empty and we have no more chunks to give? Get more memory. So we get more memory, right? Chunk that up. And we don't actually even need to chunk it up because we know the exact memory locations. Because if we know the start, we just split it up into equal size chunks and we know all those memory locations and we just store pointers to them, right? Or you can even store indices. I'm not sure exactly how they implement it, but you can think of any of those things, right? You don't, this demarcation that I'm doing is all just silly. Yeah, so then you just add now to your what was empty free list. And so this is where different slab allocators will call this a magazine of like this slab of memory that you've gotten. You've broken it up, and like I don't know if it comes from like guns or something, but that's kind of what it makes me think of. Like you're reloading with a fresh magazine that's full of memory you're just ready to give out. Boom, 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 boom. That's the thing that comes to mind. Like, I don't know. I just read these things. They don't tell you why they call things certain things. Like, what else could it possibly be? Could a magazine be? Yeah, a magazine that you read? What does it have to do with giving away, like, out things? Cool. Okay. So, yeah, this is, like, literally at the base layer, this is kind of all you would need to do something like this, right? Now, how does it compare to Linux's slub allocator? Similar-ish, right? Can you tell me, or tell the class?
Instead of zone caches, I don't know if this is the case, but Linux, or I don't know if it's the case in Linux, but Linux, they store the free list in various chunks.
Oh, in the chunks.
Yeah, there's metadata in the chunks.
Interesting. I don't think there's any metadata stored on these chunks, which is very nice for out of bounds writes. So when you, this is, I mean, we were going to get there, right? But if you then do have a, I can use like colors now.
Does that make it harder though for exploitation because then you don't get the
Exactly. Yeah. So the one of the nice security designs is now the metadata is not stored in line, right? Like glibc, you have metadata that's stored here, and you have metadata that's stored here. So therefore, if you have an out of bounds write, you are now can alter that metadata, which then messes with the allocator. We have to look at it. I am 90% sure that doesn't happen here. There is no metadata stored in this chunk. So it means that when you have an overwrite, while you can't change metadata, you can mess with the objects that are after you. So that's the main, just like on most things, you want to get the correct object there that you can overwrite and change the properties of that object. So then to get you to do what you want to do, right?
I don't think this love stores metadata at the start. Yeah, the mitigation, they have like a security config, they'll provision of them. Yeah, like the free list pointer is like the name of the object.
Oh, interesting.
And they also not mangle it, but they but he was saying like yeah, this is like the manager of libc with the size and the next pointer.
Yeah, I'm fairly confident there's like no additional metadata on this page. It's like just I thought you were gonna say, I think this, like this free list does have to be stored somewhere else. So there are like, there's like a very complex, which I don't understand, but there is like, you have to allocate memory for these things. Like the VM, like the zone management has its own dedicated memory region that it gets stuff from because you have this problem, like you have to allocate things. So, but I could also be wrong. I think it's definitely possible. Cool. All right, cool. So we went over all of these. And so, zone allocation. So we're going to look at this. It's basically like you basically grab a page of memory, ask a page of memory from the system. Interesting tidbit. Pages are probably larger than you're used to, if I remember correctly. There's this handy dandy. So sysctl. Actually, let's look at this. There is. Yeah, get page size. No, there's yes, sysctl. So, well, anyways, there's a bunch of kernel information that you can get from user space without even being root. I want to show you where this actually is. So this is more the metadata about it. So this shows you the page size of the system. So most, let's see if I remember correctly, I think the x86 based systems use hex 1000. I can't do the, is that 4096? Yeah, so I did do that one, right? Anyway, so most of the x86 based operating systems use hex 1000, and the ARM based systems all use hex 4000 size pages. I have no idea why. Maybe there's a good, I'm sure there's a great reason for it somewhere, but it's at least interesting. But I want to find out where, because it is cool. They have basically macros that allow you, like, yeah, where is, no, vm.page size. No, these are tests. I don't want tests. I want, come on. No, this is the same thing we saw. these are the names, but I thought we could find it quickly. sysctl proc. So this macro defines everything that we just saw of what are all these sysctl. So this is actually just literally wired up, I believe, to this page size compat variable. So this gives us that whatever is in that memory location, which is the page size. And these are all things that tell you, like, this is read, so you can only read from it. You can't like try to set the page size to be a different thing. So I can't remember what this is. I don't remember if this is like some size or struct thing. But yeah, this is the name of it. So you can figure out where all these syscall things, like what you can actually do and what things they tell you based on this macro, and you can look it up. So anyways, it's kind of interesting that this is how that's all done under the hood. Okay, but this shows us so the page size on our system is this much. I wasn't looking at Twitch. I'm sure people are just dying to ask questions. And okay. So yeah, just like we said, right? Grab a page of memory, split the page into size objects, and add each of those to the free list. So now you have a sweet free list. You can just give out page size divided by element size, and you have these many in your cache that you are ready to give out. And let's look up this. So there is zinit, which then calls this z create ext, which you can't see in the thing. See, I'm learning, I'm getting better. Now you can see. Okay, this was z init, which says the size of an element, the maximum memory to use, the allocation size, which is not used, and then a name. So this is what we saw in zprint. Each of those names is what's passed to here, and that's what's output there. So we have zone create, and zone create just calls zone create ext. And so we can actually see calls to this. vm.permanent, right? Let's look up so the name, VM permanent, the size 1, KMA flags, not sure what that is, zone permanent. I do not know what that does in this context. Is this a unary XOR?
Wouldn't that just be... It's just not creating this structure.
Is it creating a structure? Yeah, I see
the C there.
Yeah. But I don't know if I've ever seen this before. Anybody have the KNRC book that you can look up what the hell the syntax is? But then what is it?
The monstrosity.
See, we learned together. I don't think so. And the macros were using it, it looked like. So I was looking for this. There's this kmem range register dynamic that like does this.
Is this Objective C?
No, straight C. No Objective C in the kernel. But now I'm like wait. The type is here. Okay, can somebody ask ChatGPT what this is?
Exactly what I did. I'm still confused. It refers to a block. It says Objective C Objective-C and sometimes C/C++ within Apple's ecosystem.
I was gonna say Objective-C blocks are like.
It says blocks are essentially closures similar to a nonce function.
Yeah. Okay. What the? Okay. XNU.
They use like custom toolchain to build this.
They use Clang, but their own fork of Clang that has some proprietary things, one of which we're going to actually look at so that they can implement this new kernel that...
Yeah, it seems to be an Objective-C block.
Oh, okay. Blocks are a... Wow, this is fascinating. All right, we're going down this rabbit hole because this is fascinating. All right, non-standard extension added by Apple to Clang's implementation of the C, C++, and Objective-C uses a lambda expression-like syntax like closures. Wow. This is wild. I mean, I think it's cool, but it's also like...
When did they add this? I wonder when this like became part of the release.
I mean, this says macOS 10.5 and iOS 2.2. Oh, yeah, you're right. I think it's 10.6 and 4, which is very old.
That's probably like 2010 or something.
Maybe.
But yeah, imagine being like, yeah, I don't think C has what I need, but instead of using a different language, they're just like, we'll just implement it in the compiler.
Modify Clang.
It's just fascinating. I've never actually even seen it. Like,
probably because Apple's the only one that knows how to like use it with one.
Maybe, yeah. Wow, it's like legit closures. That's wild.
They were just so C++ or Objective-C build that they needed to like implement that specific functionality.
Yeah, maybe. But now my question is, like, how can we grep for this? I want to see if this is used anywhere else because this is like maybe like this. Yeah. Let's look at this. Yeah, I think space. Okay, this is gonna be an insane thing to grep for, but.
Oh no, but you don't want the right parenthesis close because I think that in between is where parameters are.
Yeah, I just want this space, space, caret, and left paren.
Do you see how these look in assembly?
Yeah, I mean, actually, that's a great question. Okay, so it's got tests, security stuff, Mac base, IPC, so imports. Why did nobody point this out when we were looking at port stuff? What's this? I guess we didn't look at this. IPC pset allocate name. Oh, this is so wild.
So it returns the lambda there? Is that what's... No. The lambda gets fed
is this. Yeah, the lambda, I think it should be like a function pointer that gets passed in, but like closed around any like things that reference it. But yeah, okay, so I don't think I'm supposed to say your names on stream, but for the nice people who decided this, okay, zone init. Oh, this is cool. So this is the global initialization of the zone allocator. So this is like what runs to allocate everything. That's why we saw, this is what I said with like, there's this crazy boot up that happens and like, this is this VM permanent that gets created. So we should be able to see this like get passed in, right? Of this zone T, and then this permanent gets set to true and this element size. So let's, what was this thing called? Extra setup. Yeah, because I saw this in the code. If we see this, yeah, it's just like a call here that's like, if there is extra setup, then pass in this. I thought it was just a function pointer, not even really thinking about it, but apparently it's not. All right, let's fire up our handy dandy IDA. Do you guys want to see IDA 9 to see how, if it does anything different?
Sure.
I mean, might as well. Am I allowed to demo it? I didn't look at all the rules. It's red now, yes. Okay. And I'm gonna need to use, we are looking at 12.5 system library kernels. Do you want to look at the development kernel or the release one? The release may be optimized.
Yeah, development probably is good symbols.
Yeah, let's look at development T6000. Open up. It's going to need to crank, but of course this is new, so it'll go super quick. Yes, of course.
Do you want things that would make your life easier or no?
Yeah, just ignore all that extra information that you have. Like, why would I work?
It's easy.
Yeah, exactly.
It's screen glow. Symbols are for the weak. Real reverse engineers use optics on them.
No, it's a terrible idea. Use tools that make your life easier. Okay, so we are looking at, so we are in zalloc.c. Specifically, we're looking towards the end of zone init. Okay.
Why were there exactly 44,444 words?
Because that's how many I put in there. I control the simulation. All right. Oh, it needs to analyze. So it's
almost done.
Look at that. It's going. It's at 733. Oh yeah, you can see the thingy here. I don't know. Well, yeah.
How big is this file?
It is. Where are we?
It's a long time.
Wow. You have a good CPU.
Right, I don't have the Apple Slicker.
Although I guess the development kernel probably takes more time because it's bigger. 18 megs? Not crazy. Yeah, it's not as bad as, what's really bad is a kernel cache, because the kernel cache has every single extension and driver like linked into it. So I think you can specify though, IDA is smart enough when you load up a kernel cache, you can tell it which of the things you want to actually decompile, or not decompile, but analyze. What if I just hit tab? Should I report a bug? Man, IDA, you suck. Okay. The nice thing about having two versions is I can just use the old version.
This one. Oh, wait, try that again.
I refuse. Wait, I thought I did have one up. And now we'll just oh, there we go. All right, fine. All right. But now we have to do the dance, like I told you about, where we need to map everything up. But we are looking for calls to zone create ext. Okay. Yeah. Zone create ext, permanent this. Oh, cool. It actually did automatically the flags for us. I wonder why it did that. I don't think I've necessarily seen this before. And then, wow, okay. Yep, look, IDA already knows what it is. Yeah, it then passes in a struct void star ISA, int flags, int reserved, void function pointer that takes in a zone T, block descriptor, passes in an address of block literal global 95. Okay, this is a, which, Is this?
No, that looks like
I think this is it, right? This is the thing that.
Yeah, it might create an entirely separate like segment.
Yeah, it's like in this const thing.
Where does it allocate though? Was it just on the stack?
No, this is in const. I don't know what that necessarily is.
Well, the function pointer const. Where does it allocate?
Oh, this. You're right. This.
I think it just passes a pointer to this function.
Yeah. Essentially.
What pointer?
It passes a pointer to that const, which is some struct that has a function pointer here. And it may, because in this case, this is a very simple lambda that has no external context, right? It only deals with what it's passed in. It may need to like create some data structure that stores any lexical variables that it needs when it creates the block.
So like go back to the function call.
Sure.
It has to pass it to that function somehow.
Well, it's probably a raw.
Oh, sorry. You're saying this call here?
Yeah.
Yeah. Okay.
What is it passing to that block?
Let's see.
There was like that was
the address of the address of this block literal global 95. Address load into X4. Wow, this is wild.
I'm just wondering where it creates this struct. It must do it in.
The compiler does it.
No, I know, but like where in memory it creates this struct.
Which one? This one?
Yeah,
this block literal?
Like go back to the handler. The block.
The actual function.
Yeah.
No, I mean, it's compiled.
So this is this thing from C8 to E8, right? Is this block layout struct, which has this pointer. So this NS concrete global block is the first pointer, and then this is whatever this next one is. Yeah. So whatever this struct is, I wonder if we can look at this struct. Was it block underscore layout? Yeah.
I don't think so, because if you look at the naming thing, it's underscore zone underscore init, which is the name of the function that we're actually in, and then block. And
but I was thinking this struct of block underscore layout, because this must be a thing, but maybe
no,
not.
I think the block layout is like probably an LVM construct. I don't think it's a.
But yeah, we should be able to jump to this in.
So this memory is writable.
It says const. I don't remember what all the. I assume this is somewhere constant. I mean,
right.
Will be like read only.
Because like on the Wikipedia example, it looked like you could just do anything inside the block.
Mm-hmm.
So I just wonder, like,
yeah.
Don't do constants like that example. Like, where it's actually writing the struct.
So so there's the function, right? So this is the function that gets invoked.
Right.
This function gets passed in like the zone. The argument to it is the second one. The first one is some type of other thing. This block descriptor, which that is a pointer back to that same thing. So I bet one of these or this block descriptor. Basically, something in here is where you capture like any variables. Like if, so looking back at this code, right? So if this code was using in this lambda was using anything like KMA flags or something, at the call it would. Yeah, I don't know exactly how it would do it, but it needs some way to like either allocate memory for that closure, put the variables, like copy the variables in there that it needs, and then.
In this case, it's just constant.
Exactly. Yeah. Exactly. Yeah. This is a no lexical references in this thing, so it's very easy to capture. Crazy.
They just like allocate it on the stack in the function that calls it, and it just passes the stack.
The problem is you don't know your closure may outlive the stack, so you can't pass it on the stack.
According to the Apple docs, it does reside on the stack.
Oh, well then.
In the parent function, the closure should not be the parent function.
Yeah. So, which is why they kind of explicitly say don't use it in somewhere reference to this block.
Oh, okay.
Interesting.
Out of scope.
Right. If you go to the LVM project GitHub and search for block_layout, you'll find the update. Just the stock LVM. You can't. I don't. Oh well, that might. Yeah, there you go. block_private.
I think it's my first time Googling.
Maybe. I've never seen you Google on this.
This is merged into LVM.
Yeah.
I'll start using it in my project.
Oh yeah, there we go. So some ISA flag, or sorry, some ISA, some flags reserved, and then the function itself, and then the block descriptor. So what, this probably? Go to it. Yeah. Copy, something to copy it. Wow. I don't know.
Oh, that might be the stack stuff that Jay. Maybe that's like how that decides.
They have other functions to call if you actually want to use it outside of that scope.
I see. I see. Which the compiler maybe figures out or something? I don't know.
No, you have to explicitly code that.
Okay. Interesting.
Almost sounds like a bad idea. A little bit.
Yeah, it's weird to see in the kernel. I would not have expected this. I guess their compiler supports it, so why not? And if it makes it, I don't know.
They made the compiler support it.
Yeah, I mean, it's very clearly easier to do things like, hey, I want extra things to happen to my zone after I create it, and this is what I want to have happen.
Right. Make a function in the class where it exists like everybody else.
What is a class? This is C. Yeah, it is interesting. I don't quite understand why, because I think zone create ext returns the zone, so you could just like get it and then do this. But maybe there's a certain reason of why you want it to happen exactly there in.
Or maybe it's so that you can pass the zone object around and then do like whatever the thing is on the object itself rather than having to call some other method.
Yeah, I mean, there could be other stuff that happens after here that depends on those setup. Oh, I guess if it's okay, so it's called extra setup. So you'd want to have it happen when your zone is set up, but before it gets all allocated and stuff.
I don't like it.
Wild. Okay. Like 1,000 of these flags that exist? Yes.
I thought there's that, like variants of this
No,
one.
exactly. I agree. That's what I'm saying. Like you have these create flags. Like, are we running out of them that you need to do this? Do you want to look for every single instance here?
You saw how they set up their bit fields. They're insane.
That could be because we don't see all the code, right? It could be that there's kernel extensions or drivers that for some reason need to do this for special things. But yeah, if we look at like every call, well, I don't want this, but like that's a ARM. So physical map, but it doesn't use that. Null. This does use it. Yeah, see, this is doing some weird thing with the reserved elements for some reason. Why? I have no idea. This also is doing something here. This is definitely stuff you could do statically, or you could have a parameter. I wonder if anybody would talk to me if I asked them.
Like in general?
Like why? So sorry, if I asked anybody that I know at Apple why this is, if they would respond, and if I could ever use their response on stream, that was the other thing. It's more of a public thing. This is interesting though. Set exhaustible. I don't know if this is a function or if it's just a macro, but this then could be another like. So you're slightly doing it.
Wait, so is that it? But when does that function call happen?
Look at this, comments in our block.
Does that function call happen in the lambda, or does that function call happen before the lambda? Like whenever you call the lambda.
In the lambda, it has to happen in the lambda. That's the semantics, right? It's like you call this block of code whenever the thing gets called.
Oh, maybe that's why they do it as lambdas, because then you can still retain references to that, like, to those variables that exist at that point in time.
Yeah. I mean, that is what blocks and closures are for, right? So you can, it's used a lot. Like, look at this. This is super, like, this is the VM pages array. Wow, I mean, it's just wild. Yeah, I guess, I mean, this is something that you probably just wouldn't want flags for. Like, this is logic that is so specific to this instance. But, like, why? Still, I don't know, because I think...
I feel like this was one engineer that's like, I have an idea.
You know, this, as you can see, abstraction always has its cost, and flexibility has its cost, right? Everyone who uses now, if you did want to change it, like one of these nice students suggested, you'd have to implement this logic in your stupid allocator function, which somebody needed and wanted. Like, why they wanted to need this, I don't know. So you almost can't ever rip this out now that you've done this, right? You've given, if you think of this zone create ext as like an API, right? You've given people such a flexible parameter of your API that you can never change it, because, and you have to just support this. Wild. Okay. Where were we? Okay, okay, we were looking at zone allocation. This is what we were looking at. And then we got distracted by this extra setup. Names, size, flags, zone ID. So let's kind of scroll through this, checking if the size isn't too big. There's a KSAN thing in here, which is kind of interesting. Like this one's, I think this is based on name. So this is like preventing you from creating a zone with the same name. You just return the old zone. I can't think of anything where that would cause a problem if you were able to do that, but other interesting things, depending on where the kernel is in its boot up phase, there's different things that happen with the allocator. Like I can't quite understand why. I think it's like this name may not exist, and so it has to allocate a name and give it to it. Otherwise, just use the name and point it, like you can use that character pointer that's passed in. This is like creating a copy of it and allocating with this zalloc permanent, which I don't know what that does either. Maybe that vm.permanent, it uses that. But this is the thing of like, it's very, you have, everything needs memory and allocation, right? And if you want everyone to use your thing, you have to worry about where you are in your boot up process. Let's see, the element size, chunk pages. This would definitely be a thing I'd look at of like, can size be greater than a uint 16? There was a size check earlier, so that would be like if somebody's asking for big elements and then it gets shrink down. I don't think it's possible, but that's, you know, something interesting to look at. And anyways, this is all the handling. I guess as we scroll through this, maybe you see why they want to give you flexibility, because you can see all this stuff that has to happen with these flags of like, if this flag is set this thing. If this flag is set, do this. If this flags are read-only, then do all this stuff to set up read-only. If there's a per CPU cache, then set these flags, but also allocate, like check that two flags aren't set at the same time. Anyways, lots of other flags, extra setup, which we dug into, which I was curious about this morning, and now I'm no longer curious, and I see it's a giant rabbit hole. And tons of macros too, and tons of if defs, right? Of like, so you can see that there's a lot of parameters that they can play with here. And yeah. Cool, okay. So the whole point was to look at that. All right, and then, like we saw, stop, get out of my way. Allocating from a zone, so that was creating a zone. Allocating from a zone is basically the same thing. So if we have something on the free list, then return it, and that's the fast case. If not, then allocate a new slab, divide it into chunks, do all that. and that's the slow case. So let's look at this. This is, of course, much more complicated than the high-level view I'm looking at here. I think we'll find a very good zalloc. Let's just go to zalloc, not underscore. Yeah. So here we can see why the zone and the view can be the same thing, as we saw. So it gets passed in here is this union zone or view. Hello. Yeah. So for things that can take in either a zone view or a zone, wow, this is crazy. So zalloc and zfree can act on either one if you have just a view of it or the pointer to the zone itself. You can see that in here. That's why those first 4 bytes are the same, so it can do that. But interesting thing, if defined C++, what is this? What? This is I think, okay, weird. There's also this kalloc type view, which we'll see in a second what that is, but we know those have to have the same 4 first elements, so it can actually use that. And so we call zalloc flags, pass in this wait OK, and you can see there's a no block, which is no wait. So this is, again, you can see that even at the allocation points, we can have different flags that control, right? So wait OK would mean that I'm okay with blocking my task or thread or whatever it is when I'm trying to allocate more memory. If there's not enough memory, I'm okay waiting. The other call is like, I don't want to wait. So if you ever have to wait, just return because I'm on some critical thing. So zalloc flags. So we can see that from the zone or view, it gets the view and then, it gets the zone. So now we have a pointer to the zone, and then it gets the stats, the size. It does some assertions that we're doing things correctly. And then calls zalloc ext. And this is the thing that actually does the allocation. Let's look at, So this is very nice. We missed one of you lovely students pointed out that there were good diagrams in the code that I didn't show last week. And now we can see this other nice diagrams in the code. And this stuff is really helpful. So there's 4 major ways to allocate memory that end up in the zone allocator: zalloc, zalloc flags, zalloc per CPU, kalloc star, and zalloc permanent. While permanent zones have their own allocation scheme, all of the code paths will eventually go through zalloc ext. So you can see like zalloc ext basically tries to zalloc cached, and then if it can, it'll do zalloc cache fast, which should be just like we said, return from the free list, boom, and then return. But if it doesn't, then it needs to go to the slow route. And then I think by slow, then I don't know exactly what this decision point is. And then it may come up to cached fast. And I still don't understand the difference between zalloc item and zalloc cached. It may be when it can't use the cache, it needs to do something else. I don't quite know. We'll see. Maybe we'll.
Why is there also like an infinite loop for zalloc item?
Are you telling me this is not a DAG? Oh, here? Zalloc item, zalloc ext? Is there another one? I'm like going through all. Oh yeah, here. I don't know. Great question. Let's see if this helps us. The zalloc item track is used when zone caching is off. Okay, great. We at least know there's the parameter there. Zalloc item fast is used when there are enough elements available. Zalloc item slow is used when a refill is needed, which can cause the zone to grow. This is the only code path that refills. This track uses the zone lock for serialization. Okay, blah, 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 locking. The zalloc cache track is used when zone caching is on. Zalloc cache slow is taken when the cache has elements. Fast, yeah, I was like, that doesn't make sense. Thank you. Zalloc cache fast is taken when the cache has elements. Zalloc cache slow is taken if a cache refill is necessary. It can choose strategies. It can cache from depot to try to reuse CPU stash magazines. It can recache from recirc to use the, I don't know what the hell this is. Use zalloc import if the zone has enough elements. Falling back to use zalloc item if zone caching is disabled due to VM pressure. The zone has no available elements. So lots of different strategies of things that it's trying to get memory from. You can think like over the years, somebody or a team of very smart people have decided and done profiling and said, oh, this is very slow in this circumstance, therefore we should create more caches and more ways to get memory. Okay, preemption stuff, depot locks. In general, the zalloc slow code paths deal with refilling and will tail call into the zalloc fast to perform the actual allocation. So we at least know that's why there's some arrows going between, because when you call zalloc slow, you will then eventually call fast, because which is kind of nice. You're not duplicating logic. You know at that point there should be something there, and so they can go. Zalloc return is the final function call everyone tail calls into, which prepares the element for consumption by the caller and deals with common treatment. Okay, cool. Did that actually help us at all? So let's look. Case and asserts. There's a flag that's no fail, I think, is something that you can like basically say like if I cannot allocate this memory, then like panic and just shut down. Like this memory has to be allocated, otherwise we're not getting anywhere and the system should just burn. I do not know what VM tag size classes is, and I also don't know what config gzalloc is. Disabling preemption here so that we're not going to get preempted and we can actually like allocate memory. Let's see. And okay, so we have, let's look at zalloc item. I just want to see something that gives us what we said of like, we allocate some memory and then we split it up. Okay, so zalloc item. When we committed, here's your backwards edge. You ready? When we committed to the zalloc item path, zone caching might have been flipped / enabled. If we got preempted for long enough, the recirculation layer can have been populated and allocating from the zone would be incorrect. So double check for this extremely rare race here. So there you go, zalloc ext, that's how you can get here from there. So that's a backward edge. So the comment says this should never happen or very, very, very unlikely to happen and you should never see this. It would be interesting of thinking like, what's the problem here? Like, is there a way you could trigger this as an adversary to make it, because this is probably not ever tested, right? They probably fixed some bug, and that bug maybe didn't occur, but do they have test cases that test this exact path? I wouldn't necessarily bet on it, but who knows? Okay, here we go. So here's then so here we have so basically saying like, hey, if the number of elements free is less than or equal to this thing, then call item slow, otherwise call item fast. So we want to see what happens on let's go item fast, because this should be quote quote simple. Okay. So item fast, zalloc import. I don't know what that does. Does that lock it? Probably. Zone elements free sub. Okay, it increases the size, e size, and then it unlocks the zone, and then it returns it. But why doesn't it just like give us a thing? Okay, what does zalloc return do? Okay, wait. So we were at item slow. Okay, whoops. Okay, there we go. Wait, what? No, fast. We're in fast. Okay, zalloc item fast. All right. Okay. Whew. I was freaking out because it didn't look like anything was happening. Okay, this zone element T is a thing that gets passed into zalloc import, the address of it, and then it gets passed into zalloc return. And it's called the element T, so it's probably the element of some list, like an index or something. Let's double check. Let's look up the type. Where are you? Type that represents a resolved zone element. This type encodes an element pointer as a pair of chunk-based element index. Okay, we're getting somewhere. So a zone element T, oh, cool. I could actually just look it up in my handy dandy LLDB. Oh, this is, wait, what? I thought it said it encodes stuff. Is it telling me it's encoding a chunk and an offset by just giving me a pointer? Yeah, okay. Okay, let's see. The type that represents this type encodes an element pointer as a pair of chunk-based element index. The chunk base is extracted with a trunk page. As it is always page line, it occupies the bits above page shift. The other bits encode the element index in the chunk rather than its address. Okay, let's see where it's used. So we're at least making progress. So we were in, what is it? zalloc fast item. Item fast. Yeah, we can't do this for all the paths. This will just make us go crazy. Okay, zalloc import looks to be our winner. Zalloc import. We're gonna read the docs. Function zalloc import n elements in the specified array opposite of z free drop. Okay, so at least we say we have a zone. We have a zone element T pointer of the elements. We have flag, E size, and N. So we're trying to me, this would be like, okay, we're going to allocate N number of things here. So it's like a general function that you can pass in, like from this zone, like give me N number of these here. So let's look, setting I to be 0. Let's just see if we can page E index size a pointer to some zone page metadata. Maybe there is metadata about a page. Maybe at the beginning, I don't know. Zone PVA is null. Okay, if this page queue partial, meta page, otherwise page queue empty. Otherwise, we're screwed, and it says Z element free corruption. So something has gone horribly, horribly wrong. Okay, zone meta validate, the old size, the maximum size. Oh, a while loop, huh? Okay, zone meta find and clear bit, zone element encode. Elements. Okay, so elements is the thing we're trying to do, right? That's what we're writing to. So this is, so there's this page and the E index. Zone meta alloc size, add new size. If the size is greater than max size, requeue. Okay. So this is all right, man. We're gonna have to. Okay, we would have to dig very deep into here to figure out exactly what's happening to these data structures. I'm gonna pull the plug, and we're not gonna go super deep in here because we're gonna lose where we're at. The one thing I do want to look up though is this zone element in code, just to understand what's happening here. I wonder if it's a macro or something. Nope. Okay. I thought a zone element T was just a. Okay. Wait, what? Yeah, base or the index. Okay, this is just a like. Okay. But is it the index based on the size? Do you have to extract the index and then multiply it? Why wouldn't it just be a pointer? The EIDX or the base? I think the base is just like an actual pointer. But so let's look here. So page. Zone PVA to adder. Oh, no, you're right. Okay, cause sign extension so they end up with the right address. Page.packed address and shifting it by page shift.
Oh, maybe the packed address was just because a page is OX4000. Maybe they saved those 3 nibbles.
But okay, yeah, there's something weird that's happening here that.
Page shift is 3.
But is a VM? What is the VM offset type? Maybe that's the problem we didn't. Is it a 32-bit type? You think?
Oh, what's it? It's always aligning optimized.
Is it somewhere else? Everything matches it. This thing's used everywhere. Yeah, but shouldn't that be a?
So it's a.
This is an 8-byte value. So why is it casting it to a 32-bit? So it's only taking the last 32 bits of the thing and then. Okay, right?
Because it's an array.
It was. Wait, was this the one? Oh, maybe not. Where did I see that? Am I going crazy? Oh, page. When we got page, it was this one. Zone PVA to adder. Takes this page, packed address, left shifts it by page shift, then casts it to an in32, and then extends it back to a 64. F's?
Maybe they just know that the top 32 bits of the address are all that.
It could be. I mean, that.
Do they use the other bits for something? Because the only thing that I could think of is they chop off the leading 32, resign extended
to then do stuff and shove things in there? Maybe.
exactly it, because they're passing in the page and not the reference to the page, right? So it's an actual struct.
Yeah, it's okay. We also don't know exactly what this packed address is. I don't know. Like packed could be any number of things. Type used to point to a page virtual address in the zone allocator. Valid pages at the top bit set. 0 represents the null page. Non-zero values at the top bit cleared represent queue heads. Indexed from the beginning. I guess this packed. Okay. So I guess that makes sense that this is fine.
Wait, it says valid pages have the top bit set. So maybe that's why it needs to be. Maybe,
so that it signs extends it. So it.
Well, so maybe it's making sure that the. Well, wait, is the sign extension? The sign extension should be zeros, right? Or is it?
So it's casting it. This is a uint, but it's casting it to an int 32, which is signed. So it should do sign extension.
I see. Yeah.
I think this will sign extend it back, but again, this is again why actually reading C can be tricky, because what do these exact semantics do? Well, I don't know. I would look at the binary, or what I do is write exact code like this and then compile like a small C program, compile it, and then see what the resulting thing is. Yeah. Anyways, this also we're looking at 12.5. This code could be completely changed in the modern allocator, so let's not go too deep into this, but stuff happens, it gets allocated somehow, and like stuff gets freed to us, and then we get to use it. Yay! Ooh. Okay, that was slide 5. Yay! And then deallocating, we start from Z free, go to Z free ext. Basically put the pointer back on the free list. And we can look at, actually, this is something that also I was going to ask you if you've seen this. So this is kind of cool. There's, they actually define Z free as a macro. So there's zone and element. So it gets the zone. It calls Z free on this. And then it I guess I didn't look at this, but the comment says all values passed as Z free might be in the element to be freed. I see. Basically, this macro sets element to null on free. So this makes sure that there's no dangling pointers, that after you call Z free, your element is null. I think that's what load pointer and erase does. So it's kind of cool. The thing that I don't quite know why, but I'm sure one of you can tell me, is why passing a function with parentheses around it causes it not to be macro expanded or changed at all. So for instance, on the problem where I had memcopy, where it was getting compiled to checked memcopy, you can actually get rid of that with this same technique by doing memcopy in parentheses like this. I don't know what this tells the compiler to do. It must do it, and it must compile because it works.
You're saying the macro expansion doesn't do...
Here, let me show you. So this is Z-free, right? Z-free. Yeah, if I look for this, so normally I look for Z-free parentheses. We will not find it in here. And I was going crazy being like, where is this? I think this is somehow telling the compiler not to macro expand it or something, because that macro is defined right here, right? This pound defines Z free, but it's defining a function Z free that it's also referencing here using this parentheses trick. And I just learned about this literally a week ago when doing the IPC assignment.
Let's see what Stack Overflow has to say. It literally is exactly what you said. Avoid the macro.
Oh, cool. See? Look at that. Yeah, anyways, okay. So cool. Okay, so we can look at here. So the other cool things you can see are, I guess that's case analog, so never mind. gets the zone from the zoner view, figures out where to go, and then also you can see the other nice thing. Normally, well, not normally. Never mind. It's very clear that you can get the size of this address from the zone, right? So you can look at this size, like the size comes from the zone itself. So it just dereferences it, figured out the size, and then calls zfree.ext. Oh, and so now we have a new diagram on the way back. Thankfully, it's slightly less complicated. So we have zfree per CPU, kfree. Eventually, everything goes to zfree.ext, which either goes to zfree cached or zfree cache slow or zfree item. Although, what would zfree cache slow be? So let's read this. While permanent stores have their own allocation scheme, all their code paths will go through this. Ignoring the gzalloc free code paths, which we will do, it looks like this. zfree.ext takes care of all of the generic work to perform on an element before it is freed, zeroing, logging, tagging. Then we'll hand it off to either zfree item if zone caching is off, zfree cached if zone caching is on. Zfree cache can take a number of decisions. A fast pass if, these are the two magazines for allocating and free that is on the per CPU cache that we're not going to talk about, but it has little things there. Have space, using a CPU local or recirculation depot, or falling back to zfree item. Cool. Okay, so let's look at, we'll look at this, but we'll eventually get to zfree item. But where is our, yeah, there we go. Okay, zone, stats, address, and element size. KSAN stuff. See, there's like so much stuff that has to happen. If there's logging, if there's gzalloc, page meta, zone element resolve. So what was it? ELEM is the where was this? Wait, where's adder? Okay, so we need to figure out. Yeah, okay. So element is the adder just in a VM offset T, which is the same size of a void star, so that's fine. So we had page meta, so this must figure out, and I guess we also have our address of ZE, gets the page meta, disable preemption, this, and then checks if we're doing caching, then do this, otherwise do zfree item. So let's do zfree item. Okay, so this actually totally makes sense with what we saw, right? We saw when we looked at whatever that zfree other thing was, it told us that zfree drop was the opposite thing to get rid of something. Yeah, so this was zalloc import. Of course, the opposite of import is drop. Everyone knows that. So zfree drop is getting the size of the element from the zone. There's a check for a double free panic. I think it's looking at like, I have no idea what this is doing. Old size, max size, new size is 0. Then do this zone where the page queue, move it to free. So zone meta requeue, I think puts it back. Otherwise, do this. Anyways, so let's, like we said, not get too thing. The other important thing for our purposes of what we're trying to do is if there's memory pressure, then. So this doesn't happen all the time because you don't want it necessarily, but once we've freed every object that's on our page of our slab, now that page is eligible to be returned back to the operating system so it can be reused for other types of memory, right? This is a key thing because if every zone just kept holding its memory, over time that would like accumulate a ton of memory, and when there's memory pressure, you want to make sure that you can allocate memory. So other things, we saw that there are per CPU free list cachings to reduce lock contention, which we already talked about and we don't need to get into. there's a randomized free list, so the order that objects get returned is randomized. I cannot figure out where in the code this is happening, so if you find it, let me know. I do not know where it is. I think it would take us, I bet with like 3 weeks of effort together, we could like fully document how this works. But I've done that, and then they change it like in a point release, so you're kind of catching up. So what we're doing here is at a high level, we're looking at this version, and we'll look at some of the security things they've done. And then hopefully, well, anyways, we'll get there in a second. Zprint, like we saw, and I'm sure there's other features. So how do we want to, so let's talk about more generally, how do we want to exploit a kernel use after free? So everyone knows what a use after free is? Please shake your heads. Okay, good. You can leave. You're probably still taking your test from the last class. So a use after free, fundamentally, there's some pointer into memory that the kernel has freed and is being used for something else, and we can now use that. How do we turn that into actual exploitation? On the face of it, it seems very silly. Like, sure, there's a reference to memory, but like, so how do we turn that into exploitation to further our attacker goals? Not on XNU, just in general.
Use it to overwrite information. Maybe this gives you an out of bounds right.
How do you get an out of bounds right? Because you only have you have a pointer to memory that's been freed. So how do you turn that into an out of bounds right? Because from my pointer that I have, I can only write inside that memory object, right?
The pointer may also get reallocated somewhere later, and then you write to the new stuff that was allocated over.
Yeah, so it could be that something else gets written there, which then we can reference with our old pointer to do stuff, right? And fundamentally, this is a type confusion, right? So it could be that the stuff that got written was great and we can totally control it, and now we can control that object. That happens less often, but fundamentally, the idea and why this happens is because now there is a new, different type of object that gets put at that same memory location that our old pointer is, and we can either manipulate it from both directions. But fundamentally, it's a type confusion that then may allow you to do an out-of-bounds write or out-of-bounds read, or even control a function pointer, all kinds of cool stuff. So kind of the goal from getting a use after free is then we want to get some kind of type confusion. And fundamentally, the best case scenario is when we can get a control pointer, like either a function pointer or even other types of pointers are also fine, overlap that with data, right? And if this is familiar to you, it should be. This has been a problem, like code and data mixing have kind of been a problem in security forever, all the way back in like phone phreaking, when you could whistle into the phone system to get free calls. That's because the signaling mechanisms were sent over the same channel as your voice, and so they could be misinterpreted. So the goal is, so we'll consider just very carefully these two following types. So we have a struct, an IOVEC struct that has a character pointer with an IOV base and a size of the length, and we have a time spec struct. So how could we use this to our advantage? So let's say we have a use after free on an IOVEC struct.
The IOVEC struct is the thing that was newly allocated or previously?
So we have a use after free. So we've allocated an IOVEC struct. We've freed it. We have a pointer to an IOVEC struct in memory, but the kernel thinks it's gone.
So like we can target a time spec under the same memory location and like change the TV into the same parameter to some data control reference and we can use that.
Yeah, so we have a pointer to a struct IOVEC. Our goal is we want to allocate a struct time spec over that. That way we can do several different things. We can change this tvsec part, if we can control that arbitrarily, to then change this pointer to be whatever we want. And then presumably, so if you have a struct that has a pointer and a length, there will presumably be a way for you to read from user space that information. So by changing the IOV base, we can change where that points to. This is very similar to like file struct overwrites, a very similar concept, but here it's like type confusion, right? And the point is, the system does not realize that we have two pointers to the same data, but it's treating them as different types, right? It's treating this IOV base as a character pointer, but it's also treating that exact same place as a time t, which is also 8 bytes. We could also maybe not even change the character pointer and just change the TV and sec part to make size huge, and that would allow us arbitrary read from whatever we're doing. This IOVEC we may also write to, so this could be a read-write primitive. It just all depends on what this allows us to do. But this would be kind of our goal, right? Yeah, so this is exactly what we said. So how can we achieve this reliably using what we know so far about the allocator? So now specifically shifting into what we've learned at a high level about the slab allocator. On your expert pwners. Heap spraying. Yeah, so there's so depending on how it does it, okay, so the idea is we've freed an IOVEC struct, and now we want to allocate a bunch of time specs, and one of them will hopefully overlap with our object, and then we'll be good. Yeah, I don't remember all the details. There are extra things you need to do to make this slightly more reliable. But essentially the pattern of a lot of XNU exploitation is based on that. But the idea is first you allocate a bunch of IOVEC structs to take up a whole page. So you want to fill a page with all of your structs. Alignment. Yeah, that's why you need objects of this exact same size. That's why with this, and this is specifically with the slab allocator, they need to be in the same zone. If they're not in the same zone, then you can't, this will show you actually can do that. So if they are in different zones, you still can do this. And so, okay, so we have this. Which one of these is going to be freed? We don't know because it's random, right? So the idea is the randomized free list means we have absolutely no idea when we free these. Well, actually the randomized free list means when we allocate them, you could think they go in order, but they do not, right? They randomly get allocated. But we know if we allocate at least a page or slightly more than a page, we know that we're likely all on one page of memory. So we can trigger a use after free on one of them. So now we have a pointer to some struct IOVEC that points to this memory location, and it's not a physical memory address, it's a virtual memory address according to what the kernel cares about. So it's not using actual physical memory here, which will come up in a second. Then we actually don't want to necessarily allocate a bunch of time spec objects. This I think gets us into cross zone things, but basically the classic way of doing this, free all the remaining objects. So now this page is completely free of objects. Trigger memory pressure, which then makes the page go away. This is basically the cross cache stuff in Linux. Now you have a pointer to a page in memory that does not even exist. Like the kernel has not allocated it to itself. But now if I allocate a bunch of time specs, and again, I don't necessarily know which one will trigger, but if I trigger a page's worth, it's highly likely that my pointer points to one of those. And as long as now I can figure out which one, then I've won. And I have two pointers to the same object, one that's a struct IOVEC, the other that is a struct time spec. So when you read like 2021 and 2020 and 2019 like iOS exploitation blog posts, you'll see this exact structure. And a lot of what they've been doing is ports. So you do port stuff so that your port is controllable and you can make it trick you into thinking that it's the kernel port. That's one of the ways of doing it. Or I think task objects too they try to do, but anyways, this was like a classic way of exploiting things. So the key problem is that you have memory that's shared between types, right? The fact is that you can get the kernel to allocate memory that is of two different types, and that then triggers a type confusion. So let's fix it. Yay! So let's build a type-based allocator, and that's what Apple did for XNU. So this is kalloc type, is a new type of allocator. It was announced publicly on October 27th. This is the blog post. I highly, highly recommend reading it. This is one of the best. You would think for a company that normally doesn't say things publicly about how their things work, this has like code snippets and links to the source code of where things are actually implemented. So it's a fantastic read, and it also gives you a lot of insight into the real world problems they had to solve to do this. Okay. The first thing, so this, I meant to put the date on here. The release date was iOS 15, which was like 2021 was when this first came out. So it took a long time to get the blog post out. Maybe it's because they were creating the blog. But anyways, there's two key things that they needed. The first thing was basically zone sequestering. The idea being that to prevent cross-zone attacks, once memory is allocated to a zone, it never gets reallocated to a different zone. They do this in kind of a cool way. This was done back in 2020. This was the zone T struct, had this Z page EQ VA. Let's look at that because it'll be way better than this. That was internal Z. Yeah. So these are metadata structs. Okay. So list of metadata structs is maintained per page, free element list. So this has the virtual address pages. And basically, so when essentially a garbage collection event occurs, or you can think of memory pressure, right? And the operating system has to go around and be like, oh crap, we're almost out of memory. We need to start like giving some stuff back. What happens is that the physical memory is returned, but the sequestered virtual addresses are kept by the allocator. So that way the allocator essentially keeps those virtual addresses so that they're never returned back to physical memory. And that means nobody else can use them. So each zone gets exclusive access to any page that ever gets allocated to a zone, can only then ever be used by that zone. And I guess page means virtual memory in this case, not necessarily the physical memory. Cool. So now this is great because now the cross-zone attack that we were looking at can't work. Assuming that those two types are struct IOVEC and the struct timespec are in different zones, then you can't ever get a type confusion. So have we won? It's like we can go to sleep, get game over. No, why not?
Still like same type object reuse and also same zone.
Same zone reuse, yeah. Same type object reuse. That's a whole other ball game, but at least, looking at this, right? So we can think, okay, well, if they are in the same zone, then we don't even need this, right? And we didn't need to cause memory pressure in the first place, and we could have used the easier technique of just allocate, like if they're in the same zone, just allocate the other object over it, and then boom, we are good to go. So how can we solve that? You're smart people. Yeah, we somehow encode the types and we have a different zone per type. So your zone is not just per size, it is per size type. So anything that has and the question is, how do you define type? Like we're talking about structs and objects. We'll just think about like static structs and objects right now. We don't have to worry about there's all kinds of other weird stuff that happens and dynamically size things and yada, yada, yada. But let's like just think about these things. So if I gave you two structs, how would you tell me that they're the same type or not? One thing to do would be the name.
Should you use like an enum? An enum defining the...
But that's basically the name. I mean, if you have a unique... So then, okay, let's think about this. So then every... Okay, I wonder... How can I find out? Can I view, let's see, local types?
Local types?
Yeah. Is there any way to see every struct in this? Can I filter this just by structs?
I think on the right hand side, all the structs.
Yeah.
I mean, those are all the structs, right?
Yeah. So, how many zones do you want?
It's hard to say how many structs there are that are actually allocated.
I would say most. Almost the vast majority are, just because a lot of them are persistent. Like you need them for more than one. I can see sometimes for like structs that are just used for like passing data into a function are probably not, but almost all, like tons of structs actually are. It'd be a great question to see which ones actually are. I don't know how to easily solve that. I don't even know how to answer the question of like how many structs are there in here. Like, will it tell me how many there are?
If you click on the left-hand box under name, yeah, click into there, or like double click into there. Line, I think there's 14,226.
Oh, yeah, but not all structs, right? I was trying to see if this is a union. This is, I mean, there's a lot.
If you control F struct in there, can you control F in there?
You can't, no, that's only based on name, not necessarily type. Quick filter? No. Modify filter? But I want, you should know what I want. Export to header file and then grep for struct? What?
No, that's fine. Do it.
Yeah, look at it. It's just text.
One type export.
Wait, what? Where did it?
Operations at the bottom.
Control A.
Including 3 additional types.
Command A.
Got it. Got it. Okay. It was just raw in my directory. Okay, awesome. There we go. All right, look at that. Go.
Oh, but now you have those weird structs at the top.
But how many of these could I possibly have?
If I had to guess, I'd say close to 14.
Around 14,000.
All right, let's just grep. $10,000. So let's see, 10,000. Hey, there we go. It's already in here. So if we just allocated one object from all of those, we'd have to allocate an entire page for that, which would take this many bytes. How many is this in? Actually, I can't even tell if this is a large number or a small number.
It's like shifted it
Right
right by 30.
by 30?
Right to 20.
1, 2, 3. Oh, I can't just do it. Okay. It's not terrible, but we're wasting a lot of memory. I think can be very clear on this, right? If we just had 10,000 different zones, it is interesting, right? So you can think like one end of the thing is okay. We could give every single like named struct just a completely different zone. They've taken a different approach, which is based on the code data mixing basic principle. Essentially, have the compiler analyze the struct, figure out each of the offsets, like which ones are code and which ones are data, turn that into something very simple, like a string that represents it, and then that would tell you if two structs are the same or not. And then you can put them in these k-alloc type zones so that all ones of the, you can also think of it as like shape is kind of what I think about, like what's the shape of the thing? Is it just data pointer data, in which case all data pointer datas would get put into the same thing? Is it pointer pointer data, in which case those would get put into different types? They each have. So and the cool thing is this built-in XNU type signature is actually something that you can use in Clang on Mac OS stuff. So I had a thing in here, temp, what was it called? Test compiler. Let's see. So I want to see the IO vec, and what was the other one? The time. Yeah, but I'm gonna cheat and just call it excuse me. All right, so we can do this. So we can see it turns it into a string. We should actually look it up in the blog real quickly because I didn't put it in the slides. I'm just realizing of what these actually map to and what the different enums that it does and how it tries to like translate that struct to a type. But the 2 means data. So this is a pointer data and a data. And so these would get put into different types in different zones. With zone sequestering, we know we can't ever confuse these 2 again. Now, yeah, I can't believe we looked up blocks. It's like wild to me. Okay. Yeah. Here they are. So 0 is a padding. I don't know where this code is. That's interesting. I wonder if it's. Well, now I'm super curious. I wonder if it's in the code or if it's in Clang. Aha. Cool. See, it even has it in here. Given a type, the XNU types system produces a signature by analyzing its memory layout in chunks of 8 bytes, which we call granules. The encoding, again, you have to then figure out what are you going to do? Like, do you care about the thing where it's like every bit is a thing, or are you just going to group that into one thing? The encoding produced by each granule is the bitwise OR of the encodings of all the types of members included in that granule. So basically, padding is a 0, pointer is a 1, data is a 2, dual, which I don't think it's used, is 4. Maybe it is used, and pack is 8, and wait, is this more comments than are in the code? This is hilarious. Cool. So yeah, the built-in XNU type signature is a string representation of this. Of course, you'd want to do things like turn it into something more compact, all that fun stuff. And then we can look at the k-alloc type macro to see what this does. Because this is now what you want people to use. Oh yeah, that's right. I forgot this was actually very complicated, but it's okay. So we can look at kalloc type allocates element of a particular type. The other thing that now every allocation needs to specify what the type of the object is that it's allocating, right? Which can be actually a pain on the programmers. You're literally talking about the entire operating system kernel. You now have to change how they're doing allocation. So other interesting things are like creating macros or other things to make that easier for people. So yeah. So kalloc type, give it the type, the count. So there's variable size allocations, but we can look at this main one. K-free is the same way. So where's the granules? Just where is my kalloc type? Okay. All right. We won't go too into this because I want to finish in a reasonable time. But now we can do, so we're done, right? Each type is in its own zone. But do we still have the same problem that we just ran into? Instead of 10,000 zones, will there be 1,000 zones? So we still have to think about performance. The same kernel has to run on my watch, which has to run on this, well, this doesn't have it, but 64 gig desktop operating system. And so just like we talked about earlier, fragmentation is a problem, right? And so I wish there was a way we could easily figure out how many types there are. I'm trying to think of maybe if we have time, we'll go look at this and see if we can extract this somehow of like, maybe we can, I don't know exactly how to do this. Maybe we can like dump the types from LLDB so that we have all the types, or maybe from IDA, and then we can ask XNU for all the strings and then like get them into Python and then start messing with them, right? There's ways that we could do this. But basically, we could figure out how many unique types there are. Because turns out this is not feasible. So giving every type, even when you simplify it down, so rather than every single different struct has its own type, even the same shaped structs having their own type, having their own zone doesn't work. So it turns out they've come up somehow, internal stuff, but they did say they have a 200 zone budget for these. So that's how many zones that they can have. Oh, it's defined here. So let's go back and look at the code because you can't see this. And these are links I ripped directly from the blog post. Yeah, so here you have the Z security config KT budget, 200. Let's check. This is zalloc internal. Yeah, so still, although the watch apparently has 85, as you can tell. Probably again because more memory pressure, right? These watches have way less in terms of memory. So 200 and yeah, so it's used in here. Oh, kalloc type apply policy. Aha. Okay, we'll get back to this because I think it's coming up in a second. So you have 200 buckets, right? And so what's your solution then? How do you segment these types into these buckets? You just throw them in there randomly? Probably not, because your goal was to try to avoid code and data mixing as much as possible. Yeah, but how do you group them together?
Maybe by highest overlap.
Highest overlap. So compute something of like how similar are the types, or you could say how many overlaps are there. Yeah, that would definitely.
Literally just do strcmp
for instance, yeah, you could. Question would be like, could you do that at compile time? Do you need to do that?
I mean, their obsession with claim. It's probably at compile.
You could, but you definitely could because there's the linking step. But then you do have to think about there are drivers and kernel extensions that get loaded that aren't necessarily in the kernel itself, that they can use kalloc type themselves to add new types to the system.
So yeah, maybe there's a runtime. Sounds like a nightmare.
Yeah, so definitely these are all interesting questions, and they have different security trade-offs, right? Because like you said, if you just randomly threw types of the same size together, well, I don't know, maybe I got lucky and IOVEC and my time spec are in the exact same zone, in which case I'm golden, right? So I had several things. So basically, they do this at boot time, so they do this randomly. So they randomly allocate the types to zones, and they divide, like, let's see if this code helps at all. Oh yeah, this was the kalloc type apply policy. Let's look at it in here. So it gets past a frequency list. So it uses like the frequency, I think, of things in different, but let's see, okay. Ooh, nice printing stats option if you have some debug stuff enabled. Yeah, unique signature, size, zones. And let's see, a shuffled set of signatures. So this is where we're doing the shuffling of things. And yeah, it also tries, at least the blog post says that it tries to do prefix matching. So it tries to like put at least types that have the same prefix together up to some amount that they can potentially do, which helps to do that. But yeah, basically string similarity, but not using strings, because I think these get compiled down to a 32-bit or something like integer. But yeah, so that is, and then, oh wait, did we already click on this? Yeah, then this is still the same function, right? No, type create zones fixed. Wait, this is what we were looking at, right? Yeah, okay, get the shuffled set of signature. Anyway, so this is where it's using randomization to randomly then put types to different things. So, it has definitely, so what are some of the pros and cons? Break it now. From the attacker. We're the attacker.
Maybe it narrows your, like, where you need to look, because you know that certain things can only ever be allocated in proximity of each other.
Yeah, so it definitely like makes your job harder, right? Because you now use after freeze, it becomes much more difficult. So when you're looking at like what type of type confusion objects you want to try to overlap, you have to then worry about they need to be the same size, they need to have the same shape and prefix, and then depending on what size and whatever that they are, it could be then there's an additional randomness of like when you run your exploit, will they be in the same zone? Because if they're not in the same zone, then you can't do it. Or maybe you have to start thinking about multiples, like getting multiple potential objects that you can do, which would like rather than just having to have a type confusion between the one you have to use after free over and some other type, you would think, okay, what if can I get those other type? Like, are there 5 types I can use, which would increase my chances by 5 that they'll be in the same, one of them will be in the same zone? Can I tell? Like, that would be an interesting question of which type it is. Can I just try all 5 types and then use the first one that works? Yeah, other other thing that we mentioned earlier, a self overlap, right? Which was basically, which one was that? Dirty cow or whatever? Or dirty cred? Yeah. Of basically like, or you can think of, was that the one of like a file and then you like overlapped another file on it that was like a privileged file? Yes, that's right. That's right. Anyways, yeah, you could think of like, I think files are yeah, we were thinking about ports, right? So the port structures, if you were able to have your own unprivileged port that gets freed, but another processes or something's task port gets scheduled there. Now you have a pointer to that thing that is a privileged port that would allow you to escalate privileges. That would be like a very clear self type use after free that these techniques can't deal with. Also spatial vulnerabilities, right? We've only focused on use after free, but if you have an overwrite, then you can control other parts. And as long as the struct that you're overwriting, as long as the next struct after you has control data, then you can corrupt that data. Yeah. I was thinking data only attacks, but that doesn't quite make sense. But so then, yeah, elastic objects. So objects that either need to grow or get allocated. So we didn't, I'll show it real quick. There are stuff that they have done, and you can read about it in the blog post where they talk about things that they did to like try to handle that, because there's different types of elastic objects, right? There's just like, I need objects, right? I need a dynamic array of a certain shape of object, and they do, I think, try to do things where those get in similar zones. But then there's like, I just need like I got a name from a user. I just need like 1,000 bytes or whatever the bytes are, right? So that's wait, what? I thought there was, maybe I'm full of it. They used to have a K, I thought a K heap, or do they call it something else? Well, okay. Maybe these shared things are for that. But yeah, it's kind of cool. You can see here that there's like at least for even of like 512, there's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So like 512 got put into 12 different types for, whatever reason. Which types got, and like this I don't quite understand of like var1 of what these are. I thought there was like a default. Okay, let me look at this real quick. Permanent per CPU, threads read-only, Mac labels, procedures read-only, credentials, sandbox stuff, AMFI, IPC ports, port sets, K-message, proc task, threads. I think this data, so everything that's just data, I think gets shunted into here. So this is another thing, is if like, is data really just data, right? You can have different data things that are actually very privileged, like the bit that says your root or not, right? In your task, like that is technically data, but it is with other control data. But anyways, you could think of ways maybe of that a write overlapping different data could allow you to do things that you shouldn't necessarily be able to do. It all depends on like how much this, I think there it gets into like, is the data user controllable or not? And that, because if it's fully user controllable, then it doesn't matter, right? As long as you can overwrite it, but maybe you can overwrite it, but root can't, or root can, but you can't, and that would be helpful. Yeah, there's this shared stuff. Okay, chaotic types. Work queues, bank accounts. Wait, bank accounts? That seems weird. Bank tasks? Wow, just getting to work, huh? Somebody's got to bank things, you need. Yeah.
Somebody thought they were very clever with that.
Yeah, sockets. I think that's, you know, gotta have sockets.
So why did they pick 200?
Which one?
It's like 200 types of.
They don't say explicitly, but I think they say explicitly something like we did profiling and based on like modeling or whatever on the workflows we thought this was a good thing.
It's like a very arbitrary number.
Well, it's also very round, so it's not super arbitrary. Bank ledgers.
Uppercase B this time.
Yeah, this is my real machine, this laptop, so I'm not.
Yeah, let's see your ledger.
Yeah, IO kit is this is the interface that kernel extensions get to use to. So that's what this stuff is. I think it's like another like layer basically. Yeah, there's like basically a lot of these are different subsystems. Like PF is the firewall, I think. So like PF rule PL, all these things are different elements. So like this component manages its own thing. IFnet is like Ethernet and all that kind of stuff.
How does that work with the PF chains?
And yeah, where was that one? Where is it?
What?
Oh, I thought there's actually one that was called that instead of just a terrible joke. Okay. NFS, I think I mentioned this at the beginning, but NFS is all done in the kernel, which is insane. Technically, I think a kernel module, but yeah, everything in there. Okay, where was? Okay. Short answer is I have absolutely no idea. And also, this is a different version than what we were just debugging, so I don't know. But there's like, okay, let me make sure I'm not going too crazy. Wow. I said too crazy. Yes. Okay. So. Yeah, so there was this like default thing that things went into for these types of allocations. Maybe they have some completely different scheme now. We can look at, I think it's closer. Oh no, it died. Did my guy die? Oof. Okay, so this was like the default K alloc where just things went if like you didn't specify where they could go. All right, there's still bank stuff. Hold on. Anyways, we're not going to diff this whole thing, but there is, yeah. Anyways, you can check in the kernel and see where that happens. Okay, other pros and cons. You made me completely forgot where we were talking about. Yeah. So anyways, it's a super cool, you can see that like it actually tries to get to the root problem of a use after free, right? And saying like, and maybe, you know, that'd be interesting as they do these new features of like lockdown mode or something. Maybe it'd be interesting if that also just like did like every type has its own thing and just like rebooting the lockdown mode and it's just like you're wasting so much memory because you also have to think about fragmentation could be like you're allocating like you allocate a page and one object stays and you allocate like 5 pages and one object in each page stays and you don't have a way to like coalesce them or anything and it's only those types and like you just can get weird allocation patterns. That's why like having a lot of objects using the same memory is very nice because you're highly likely to be using a significant fraction of the allocated memory there. Yeah. Anyways, super cool security mechanism. I will try. I don't know. At some point, maybe we'll get dtrace working. There'll be cool stuff to work on in an hour. I think that actually will be very fun. You'll have to learn a little bit about. You'll be for the exception port stuff. You'll have to dig more into like MIG and other types of things of like because it's the you are now have a port that you have to listen for messages that get sent, and those messages that get sent have a structure to them that are defined in MIG header files and not necessarily like easily defined. You can also do other stuff, but anyways, it's like the way to start actually using these things. But it is, I think, going to be very cool to see what you can do with ports and like messing with other people's stuff. I will try to figure out if I can get either dtrace working. If not, I either then need to get kernel extensions working. I think my goal with this stuff is to have you guys start playing with use after freeze of like where you get information about, hey, maybe you get to choose the allocation or something, probably, but I will have to write a kernel extension that you have to talk to do stuff. So I don't know if that's going to take a week or 2 weeks. It may be a while, but we'll just play it by ear. But it'll be fun. We'll be popping stuff in the kernel. All right. Thank you all. Thank you all online.